Well, thank you for the invitation to speak today about LITMS. And I'd like to acknowledge our whole team, especially my partner, Stacey Nagahara, who's also on the call today and can take questions later about the heat flow part of the experiment. Rather than sort of get into the science goals first, I want to show you the sort of hierarchical layout of what is really a virtual suite for LITMS. So the first instrument, called LISTER, measures the heat flow of the interior of the moon by measuring the temperature and the thermal conductivity at depths up to 3 meters. I'll show some details of this later, but you can see on our sort of notional mini lander there, it's mounted on the bottom of the lander, and it extends its probe into the subsurface. The other measurement that we make is the electrical conductivity profile of the deep interior to hundreds of kilometers down using what's known as the magnetotelluric method. I'll have a separate slide on this in a moment, but for now, just realize that you have to measure the electric and the magnetic field at the surface of a planet. And so one of the instructions in the call was that you could not interfere or overlap with the Lucy experiment, still already mentioned by Mark. That's quote pre-manifested for this mission. They have a suite of electric and magnetic field sensors that partially overlap with what our magnetotelluric instrument would do. So our solution was to directly partner with them. We will use their magnetometer data. They have both a search coil magnetometer for higher frequencies and a flux gate, analogous to what Dave talked about for Vertex for low frequencies. The cooperation is explicit, though, in that in order to get the proper correlation between the electric and magnetic fields, we're going to take a timing signal from Lucy that we can use to correlate the fields once they're received separately on the ground. The thing that we still do is to measure the electric field differently from Lucy. Lucy has these booms that measure fields into the megahertz range for space physics and radio astronomy. We are interested in electric fields that are very slowly varying, typically at less than a hertz. In order to do that, we need ground contacting electrodes that are spread much farther apart. And I'll show you that mechanism in a moment, but they actually will go 20 meters away from the lander for a tip-to-tip distance of 40 meters. The advantage of using heat flow and electrical conductivity together is that, as illustrated in the data flow diagram, this will help us separate the temperature and compositional dependence as intrinsic to each. So the heat flow is a boundary condition that you can generate a temperature profile from. The electrical conductivity, you can generate a temperature profile assuming you know what the materials are. And so by using these together, we can help deconvolve their dependencies. Now, I will point out that we can't tell difference between, say, olivine and pyroxene, but where the electrical conductivity is sensitive to the total iron content, or reciprocally the magnesium number. So we hope to understand something with the magnesium number of the mantle beneath the landing sites, and then also water content. The hundreds of ppm are inferred for at least parts of the lunar interior, perhaps especially those associated with pyroclastic volcanism. And so the water content is something we'll also be sensitive to at significant depth. An advantage of both of these approaches is that we can do these experiments within the daylight mission that's allocated. So it's critical for the seismometer to be able to last longer, but we're confident we can get our work done in the 1 to 2 weeks of the landed mission. Let me just say a few things about MT. It's a passive method. We're measuring natural low-frequency electric and magnetic fields. It's been used on Earth since the 1950s. It's basically a version of Ohm's law. You're determining resistance from the ratio of voltage to current. The electric field is determined by the voltage drop between widely spaced probes, and the magnetic field is actually a measure of the total current flowing. But we get this resistance or resistivity as a function of frequency. Each frequency has a different effective skin depth in the ground, as illustrated in the lower left. And so from that, you can reconstruct the profile of resistivity or conductivity with depth. This is, like I said, it's been widely used on the Earth, but it's new to planetary science, and it's going to be better than prior measurements at the moon, which were done using something called the magnetic transfer function. This is where you just compare the source field, the distant measurement was done by a spacecraft called Explorer 35, to a surface measurement, and at that time was done by Apollo 12. And you can derive what the induced field is, and hence what the resistivity structure is. The advantage of MT is, of course, we don't need this distant observation. And more importantly, it's largely insensitive to plasma distortions that are introduced by finite plasma wavelengths. When the wavelength in the plasma becomes comparable to the circumference of the planet, you start to get higher order effects that never were satisfactorily taken out in the earlier data. For us, this means that we can probe at shallow depths. The higher frequencies have shallower sensitivity, and so we should be able to get at the moon between depths of maybe 100 kilometers down to 800 or more kilometers, really resolving that critical upper mantle region. Here are LISTER, the heat flow probe on the left, and LMS in a different incarnation on the right during some prototype testing. LISTER is a really novel instrument in that it is a pneumatic drill. It does not hammer, it does not rotate, it just inserts a tube and injects gas, high pressure gas, that blows the regolith out of the hole. So you can see some tests at Honeybee being performed on the left. The one in the middle bottom there shows the plume of debris coming up and hitting a dust shield. And then you can see the pile of debris that's produced. In this particular test, they're using some rock chips of centimeter size to show they can loft those out. There's also an approach to dealing with somewhat larger rocks that they call dithering, where they will move the tube up and down while injecting gas, and this, trying to work the flexible tube around a rock. If you get into a rock that's much bigger than you can go around, then I'd say you probably landed in the wrong place. On the right is LMS under some prototype development for Europa. It's the Europa magnetotelluric sounder going in the thermal vacuum at the top. And on the bottom is a sequence that shows our novel electrode deployment system done by Heliospace Corporation. So the little gold thing in panel B that's ejected is the electrode itself. That's the voltage probe. And then there's a place where the cable is wound around it, and the whole thing is released by a spring that's held by a non-explosive actuator, a frangibolt. So these will be held in place until they're deployed on the planetary surface here at the moon. So now I can talk about our science. Our science is pretty aspirational. We really think we can go after some basic questions about the moon. And the first one is vertical differentiation. So, you're all aware of the basic primary differentiation of the moon. The fractional crystallization in the mantle led to stratification. That is thought to be unstable and should have overturned, mixing the interior. But there's a very interesting paper by Moriarty and colleagues that came out last year that, looking at SPA, they suggest that the uppermost mantle is still stratified iron-rich cumulates, and indeed is creep-rich. So that suggests that the creep was globally distributed, and that the overturn may have been incomplete or sluggish, at least at the time that SPA formed. So we think we can distinguish at least these two end members in electrical conductivity. In the bottom panel there, the red profile is a well-mixed mantle. There's an assumed temperature profile, but it's all uniform magnesium number. And then the green profile is a stratified structure from this Johnson et al. Paper that's stratified by magnesium number, by iron content. And you can see that there's layering and inflection in it, where the conductivity is higher at shallow depth and lower at greater depth because of the uneven distribution of iron. And then, just as I mentioned, we would anchor this profile with the heat flow measurement. Our second goal is to look at the lateral asymmetry of the moon. You're all aware that the Maria are concentrated on the western near side. That's what gives us the man in the moon. We know this is a region that's rich in thorium and from Apollo incompatible elements, creep. This is thought to be related to the dregs of the magma ocean, but we don't really understand what the interior structure is. Mark Wazorek and Roger Phillips did a paper 2 decades ago now where they modeled a large thermal anomaly in the upper mantle beneath PKT that explains the heat flow at Apollo 15 and Apollo 17, as well as long-lived volcanism in that region, but doesn't really satisfy the gravity and topography, namely that there's no real anomaly, whereas this large thermal anomaly should produce some observable signature. Some years later, I published an alternative model where the creep is basically confined to the crust, and that I can reproduce the heat flows at Apollo 15 and 17, but not so much of the long-lived volcanism. And so understanding what the mantle structure is beneath PKT, whether it's hot or cold, is important. And the way we can do this is by measuring these parameters far away from PKT. We have the heat flow on the edge at Apollo 15. We have a electroconductivity profile at Apollo 12. If we get far away, especially at a place like Schrodinger, we can understand what the true background of the moon is, and then see if PKT is anomalous at depth or not. Our last objective is to understand thermal structure and evolution. You can write the heat flow of the moon as a combination of contributions from the mantle, the crust, and a creep component. And assuming that the creep is proportional to what we see at the surface, there's some absolute scaling factor we'd like to know. But if it's proportional to that, we can solve for these three from using Apollo 15, Apollo 17, and Schrodinger, assuming that there's one background contribution. If there's not, then that's where the electrical conductivity comes in a particular way, is by understanding the difference in mantle temperature between the two from the electrical conductivity. We'd also like to look at the thermal profile. Thermal evolution models make predictions based on the total heat budget and the mantle viscosity. So the slope of the stagnant lid can be well constrained from heat flow, whereas the temperature of the convecting interior will be determined by electrical conductivity. We should be sensitive down to about 800 or 1,000 kilometers. So we will get into that isothermal core down there. What about Schrodinger? Well, this was selected by NASA as a result of many scientists putting a pool in of places they'd like to go to. There's a lot of great geological reasons to visit Schrodinger, but it turns out to be a good geophysical site as well. As I mentioned, it's far from PKT, so we can really establish those background properties of the mantle. The peak ring structure gives us 2 different choices of crustal thickness, both of which are different from prior landing sites, and thus will help the heat flow problem. Of course, the final site will presumably be negotiated among all the payloads. It's on the rim of SPA, which is an even larger probe into the moon, as we talked about earlier. Interestingly enough, the electrical conductivity measurement is sensitive laterally to a depth comparable to its it's laterally sensitive to a distance comparable to its investigation depth. So picture sort of a cone. And that means that if we're probing down many hundreds of kilometers, part of that signature will come from SPA. And because we measure in orthogonal directions the electrical conductivity, we can determine the anisotropy of the response and see if there's a different response coming from SPA. Lastly, there's local pyroclastic volcanism. Of course, the thermal anomalies long decayed since the Imbrian, but as I mentioned, water is there's sensitivity to water in these electrical conductivity measurements, and if there's a source zone, we may be able to image that. We picked Schrodinger for these reasons, and specifically because it's not Reiner Gamma. Reiner Gamma is about the last place we'd want to go, at least in the early phases of these experiments. While Vertex, I'm sure, will do a great job in characterizing those fields. They will perturb the sort of plane wave nature of what's coming in that we want to use in the time variable fields, and also those strong fields will take us out of the very sensitive gain range that we want to use in order to make these time varying measurements. So to wrap up, I kind of alluded this to earlier, but both Lister and LMS are previously and independently selected under CLIPS under the LSIP program for the 19D mission. And it was indeed our serendipitous selection that got Seiichi and I to want to collaborate both on this mission and for PRISM. The 19D mission also has a retroreflector, another important element of a lunar geophysical network, and the PRISM launch will probably not occur until 2025 in order to meet LUCI requirements for radio astronomy. Mark talked about the seismic suite. We were equally thrilled that we have sort of a complete geophysical package here of the kind that we've been talking about for the LGN. And although the LGN, of course, has to be competed, it is a big step beyond what we can do under CLIPS, principally for seismology, but also we'd like to do longer term monitoring for these other techniques, as well as go to our primary sites for LGN, which would include something in the far side, at the thickest crust, someplace like the middle of Mare Imbrium, where it's in the middle of PKT, but there's no creep. So the constraints are different under what we could accomplish synoptically under LGN versus trying to build up as much as we can under CLIPS. So it's going to be an exciting time for geophysics on the moon, I think, among these two missions. And we look forward to working with everybody. So thank you very much.